The opinions expressed in this presentation and on the following slides are solely those of the presenter and not necessarily those of ASME. ASME does not guarantee the accuracy or the reliability of the information provided herein.
Hello, everyone. I'm Colleen Kennedy, a volunteer with the Oregon section of ASME. I'd like to welcome you to our event tonight, a presentation by Wil Allen of JPL. Before we begin, I'd like to remind everyone that you can find more events from the professional sections of ASME at asme.org and find the calendar of events. Here you can filter even just for section events. There are over 100 local professional sections with volunteers like us who serve the engineering community by planning and producing events like this one tonight. During the presentation, please type your questions in the chat window and they'll be asked at the end. And now I'll hand it over to the chair of the Oregon section, Trevor Scheck, who will introduce our speaker. Thank you.
Well, thank you, Colleen, and welcome. Good evening, everyone. I'm excited to see so many new faces in the Zoom gallery tonight. I'm glad all of you could join us. My name is Trevor Scheck. I am the current chair of the Oregon Professional Section of ASME, and it is my honor and privilege to welcome you to our virtual dinner meeting tonight. Please pour yourself a nice cold beverage, give yourself a comfortable portion of whatever leftovers you've reheated, and enjoy this evening's event. And be sure to tip your waitstaff. I'm very lucky to introduce you to our speaker, Wil Allen, tonight. In honor of him, his team at JPL, and all the many people who contributed to the successful landing of Perseverance, I have decided to augment my traditional collared shirt with this Mars Perseverance t-shirt. If you likewise have spirited t-shirts, please wear them and show them in your video. However, before I introduce Wil, I want to make a few announcements. First, as Colleen mentioned, please ask your questions in the chat. If your question pertains to a specific slide, be sure to include the slide number. We will be monitoring the chat and will ask the questions at the end of the presentation. If you heard something especially interesting, share that in the chat as well. Also, please remember to keep yourself muted until the Q&A at the end. After we finish asking questions from the chat, we will allow you to ask questions directly, time permitting. We will be recording tonight's event, so if you'd like to rewatch the lecture, you can check out Oregon ASME's YouTube channel. In addition to other events already posted on the YouTube channel, we will be uploading several recordings soon. An excellent lecture by local engineer Mark Lisson on failure analysis, and a presentation about the National Institute of Standards and Technology by former ASME President Dr. Saeed Jahanamir. Lastly, to the Oregon section members that are here tonight, think about ways in which you can contribute to the mission of ASME, which is to advance engineering for the benefit of humanity. There are many ways we can work toward that goal within our jobs, within our personal lives, and within the Oregon section of ASME. Our leadership team is in the process of planning for next year, and we need new ideas, new volunteers, and new leaders. We also need speakers to lecture on technical topics. Serving with the Oregon section leadership team has allowed me to learn skills I wouldn't have learned through my job, and it's been a very rewarding experience to meet and work with so many students, professionals, and industry experts. I encourage all of our members to consider volunteering for a single event, for a program, or as one of our leadership team members. Please email us at oregon.asme@gmail.com. We would love to introduce you. As I mentioned before, I am very excited for tonight's speaker. When I was about 10 years old, Mars Pathfinder delivered Sojourner to the Martian surface. Sojourner was the first wheeled vehicle to rove another planet, and the images of the rock formations of the Ares Vallis that it sent back captured my imagination. Images taken by the Pathfinder lander of Sojourner as it rolled away from the landing site captured my imagination as well, and I have forever been fascinated with exploration. 24 years later, a new generation of children will be inspired by the audio and video of the first helicopter to fly in outer space on Mars. A helicopter aptly named Ingenuity deployed from the Perseverance rover as the two craft embark on the Mars 2020 mission. For every turn of Perseverance's wheel and every rotation of Ingenuity's blades, There was an immeasurable effort in design, engineering, problem solving, logistics planning, and creative thinking. Tonight, we will get a behind the scenes look at how JPL engineers under unique architecture constraints were able to successfully deploy the latest Mars exploration craft in a talk titled The Road to Perseverance, Mechanical Design via Product Lifecycle Management and Architectural Reuse. We are doubly lucky because our presenter is none other than Wil Allen, Senior Engineer at NASA JPL. Wil is the Mechanical System Design Lead for the Mars missions and Systems Design Lead for the rovers Spirit, Opportunity, Curiosity, and now Perseverance. He managed the development team for the 70mm Deep Space Network antenna and managed the mission support for Galileo. He spent 10 years working on the Cassini mission from design cycle to start and finish, and one of his projects now includes the Mars Sample Retrieval Lander. Mr. Allen is an application expert in PLM, which stands for Project Lifecycle Management, and tonight's talk will be about how he oversaw the design, adaptation, and part reuse in the Mars 2020 Perseverance mission using PLM. Wil earned an engineering physics degree from the Oregon State University, and now his creations are on Mars. Wil, you've done Oregon proud. Thank you for being here tonight. Let's all give Mr. Allen a round of virtual applause as I hand the Zoom presentation over.
All right, first of all, I'd like to thank you guys for having me and giving me the opportunity to share something that's been very exciting for us over at JPL. And, you know, these sorts of things just don't get old for us. So we appreciate the opportunity of sharing them. Again, my name is Wil Allen. Formal name is William Allen. Therefore, I get called a lot of names. People at work call me Bill, and everyone else outside of that call me Wil. And so those are the nice ones. So either one will do. And I work at Jet Propulsion Laboratory. One of the unique things about JPL, it's a partnership. It's a NASA center. There's 10 centers across the country for NASA. Each one has their own charter, their own name and function. And our charter is deep space unmanned exploration. And so that's what we do. We'll cover more as we go. This is kind of an overview of some of the things we do in that charter. As you see, we do several types of missions. There's flybys of spacecraft where we'll fly by an object, be it a comet, asteroid, a planet, and so forth. We do orbiters, and this is in order of complexity, by the way. And to go into orbit around a body or a planet is more risky and challenging than just flying by. More risky than that is actually landing on a planet. And as you see here, here's an example of a lander. We've done lots of landers, many planets. And the hardest thing to do is to actually rove a planet. And landing a rover on Mars has been very difficult. A lot of nations have tried, and these are the only examples of rovers on Mars driving around at this point. So it's been very difficult, but we continue to persist. We're a unique NASA center in that we are somewhat of a red-headed stepchild. Of the 11 centers across the country, we're the only one that's in partnership, if you will. It's NASA owned, but Caltech operated. So it's a weird relationship, and people ask me to explain it all the time, but that's the best explanation I can come up with. We're NASA owned, Caltech operated. So what I want to give you is a kind of a sense of how things are laid out at JPL. So here's a look at our PLM, or product lifecycle management, which is essentially an organization of our tools and the information that is produced by those tools and people, and how we store them and share them and collaborate with them. So this is quite the eye chart. So I'm gonna just step through it pretty quick, and I'll try to explain as best I can. I know this part is a little bit dry, so I'll go as fast as possible. If you have questions, feel free to, jot them down for later. This is, again, just a look of what it looks like in that PLM architecture at JPL. In the center, we have a central data management system. We're currently using Team Center. We built a framework on it called EPDM, or Engineering Product Data Management. And we capture all kinds of data in the work that we do. That work is collaborated between many systems. I work in this bubble over here, mechanical systems engineering. But there's, like mission assurance over here, software engineering, systems engineering, enterprise resource planning, electrical systems engineering. We cover the gamut. Pretty much can do everything in-house, but we always partner with outside agencies, whether it be other NASA centers, other space agencies like European space agencies, universities, scientists at other universities. So our work is always collaborative and through partnership to some degree. So in this bubble is where we're going to spend the rest of our time tonight, in the mechanical systems engineering realm. And I particularly work in the mechanical design environment in this mechanical systems engineering. So we'll move on to that and see what that looks like. This is the center of my world. We create a master model design throughout the design lifecycle of a project like the mission for Perseverance. And as we create that data and mature it, we collaborate with these sorts of organizations that are part of mechanical systems. We have to work with analysis folks. That could be thermal analysis, dynamics, structural analysis, several organizations within that. We produce content from this mechanical design environment. And by mechanical design environment, you guys are probably familiar with the term CAD, or computer aided design. That's what's at the core of this system. We use that environment to do trade studies. We have to create support equipment. We do all sorts of simulations and inspection data after we've manufactured it. We provide directly from this environment manufacturing data so that parts can be built. And so manufacturing and inspection kind of work together. And then finally, in the ATLO environment is where we build and test our spacecraft. We have to, we test subassemblies and put them together with a larger system. And we have to test and verify and validate requirements at those high levels. So it's push and pull throughout in this environment. And so on to the mission, the Mars 2020 mission. And I just want to clarify here, I'm calling it the Mars 2020 mission. That's the name of the whole project and the spacecraft. Perseverance is just the name of the rover, but it takes a whole village of people and hardware to get that rover to the surface of the planet. So you'll see all of that here. So Mars 2020 came about after we landed the previous rover, Curiosity, or the Mars Science Laboratory spacecraft and mission. Once we landed that and had some success, NASA wanted us to take that same architecture removed the 10 science instruments that were on board that, put 10 new science instruments on board, reusing that architecture, and we should be able to do all of that at a reduced cost, significantly reduced cost, and schedule. And so they thought that would be an efficient way to get the next level of rover on there to produce what we needed. So we call that a reuse mission or re-architecture. The idea was to reuse as much of that previous mission as possible, redesign some things when needed and approved. And I say approved because once we agreed on that deal, they held our feet to the fire, meaning they watched more closely the cost of this mission more than any other mission I had ever been a part of, because we had agreed to a very reduced cost and schedule. So they're going to monitor that closely. So we had to have permission to do anything and everything. And by that, I mean, we actually had situations where we were going to reuse this thing from the previous program, but in the build process of the previous program, we had to fix this. So we know what went wrong. We know how to fix it. We fixed it then. So on this new program, let's just start and include that fix in the design. They're like, nope, we want you to actually rebuild it as it was the first time, fix it like you did the last time, and then use it. So there were cases that were that extreme. So they were very conscious about cost and schedule and those resources we promised. New designs required the most amount of approval. And we did have to accommodate some new technologies, and I'll get into some of that in just a little bit. The combination of all of this was far from the language of what we sold, re-architecture or reuse. People tried to call that build to print. It was far from that. In fact, it was actually harder than building it originally the first time. And you'll see some of those reasons why as we go on. But we were able to deliver it at a reduced cost and schedule. So here's what the previous mission looked like, MSL, again, Mars Science Laboratory. And our approach, at least for starting out, how we were going to approach this reuse. So we were going to reuse the cruise stage. That was pretty much as is. That was the intent. We knew we needed a bigger parachute because we knew there was going to be more mass on the rover. So we needed a bigger parachute. So we knew that from the beginning. We intended on reusing the back shell as is, minus some minor updates. We actually had a spare descent stage. And by spare, in order to meet the schedule, the testing schedule on the previous mission, we built 2 of them and were able to do the testing in parallel. So we had this one left over, and we were able to use most of that as a starting point here. That was a significant reduction in resources. The rover was the wild child of the bunch. We knew that was going to have the most change. We were able to maintain the same logic and architecture, but there was a lot of updates we had to do. And we actually had a spare heat shield. Again, same type of thing. In order to accommodate the testing schedule of the previous program, we built 2 of them, and we're able to do different tests at the same time. Some of the new things, on top of the 10 new instruments, we had new requirements. We had to actually collect and process samples and cache them in storage tubes for the next rover to come along and collect them and send them back to Earth. Well, what you see on the screen here, this whole area, that's the rover sample processing region of the rover. We did not even have that on the previous rover. So on top of everything else, here's this new element that we're adding to that previous rover. And that's what it looked like in the CAD environment. This is the actual hardware for real, what that sample processing plant or system looks like for real. That's an actual photo. Some of the technical challenges with this whole process, rover growth was needed immediately to accommodate the new set of payload and new technologies like I'm showing here, plus some others you'll see it in just a little bit. So we actually grew the rover in all the wrong directions to start with. And of course, that ripple effect caused some of the challenges that we'll get into in just a bit. Some of the new challenges or new challenging requirements due to the sample to be returned were challenging. The level of cleanliness that came with, since we're going to return those samples to Earth, the level of what we call planetary protection and contamination control really was a significant cost upper on this program. Suppliers and their equipment for several designs were no longer available. And we'll talk about that a little bit more in a minute. The EDL, or the entry, descent, and landing parameters and requirements had changed significantly. And again, due to different mass and requirements, time of year we were landing, the atmosphere is different, different times of year. And then for fun, we threw on, eventually, not in the beginning, we didn't, these last two were not part of the deal in the beginning, but we eventually added a helicopter and some EDL cameras to record that whole EDL event. Keep in mind, we had never physically seen EDL with our eyes. It's always been in simulations only. And so this was going to be a first. So you mix all that up, and that was our going in posture for the new Mars 2020. And here's a CAD view of both the previous MSL and how 2020 ended up. And if your eyesight's as bad as mine, or you're squinting, or you have a tiny screen, these look the same. So on paper, you might think, oh, well, this should be easy because they look the same. It's the same thing. Not at all. Some of the challenges that came just from the reuse process. First of all, JPL, our business base was not built for reuse or re-architecture. We were in the one-off prototype business, meaning we built something that was unique. Our charter with NASA was to do R&D, lead that front edge. There's no return on investment with what we do, so aerospace industry is not going to do this. And so we do one-off, launch it, never get it back. So there was no need to really take care of reusing it again, because that's never coming back. We're not going to fix it, redo it, we're on to something new. So this was new for us, for our business base. Reuse needs effectivity to work properly. Effectivity being, okay, maybe opposite to our prototype business model is maybe a car manufacturer like GM. They're going to build 50,000 of those cars. So they're going to build 50,000 of all these things we're showing. They better keep track of it. They're going to serialize it. They're going to keep track of, well, serial 1 went into this version, so forth. Well, we don't do that. We build one. So we didn't have that sort. Well, if you're going to reuse, you need effectivity, and you need to know where things came from, where they're going. So we had to create a poor man's effectivity system. You can't create effectivity after the fact. It's just the way it works. We needed to preserve that MSL design while reusing it. This was becoming a trend from NASA. They're wanting us to redo an entire thing or part of it. And so if we didn't have good records preserving what we did, then we would be in trouble. So now we're trying to preserve that thing we did, but use it and turn it into this new thing while preserving that. So that was a big challenge for us. Historically, we didn't preserve designs. We would reuse them in the sense of harvesting organs. I know that's a horrible analogy, but it's really true. It's like, okay, that spacecraft is gone. We're never getting it back, but here's some spare instruments they use. We're going to just take those and put it on this, but we're going to modify it to make it fit what we're doing over here. Or we're going to change the design on that thing so it works on our different mission over here. And when you change that design, you never get back to the old one. So we had to stop all of those former behaviors and operate in this new train of thought. That was difficult for us because that's not what we historically have done. And to manage that chaos, we established a change control board, or CCB. And normally, the challenge with this was we established a CCB from the beginning, phase A of the project. And we have several phases, phase A, B, C, D, E. You know, D and E are launch and operations. A is your initial concept. Then you have implementation, then you have detailed design, and you go into fabrication. So that's kind of how our phasing works out. Normally, a change control board gets involved in around the phase B, phase C area where you've committed to a design, and now you go and start making, you know, fabricating and purchasing and producing that design. And you can't have people changing those things once you start building. So a CCB would say, you know, they would monitor, hey, we need to fix this. We found a problem. So you'd have a change control board doing that, you know, late in the game like that. Now we have a CCB monitoring things from day one throughout the whole process. And I happen to be on that board as well. So we were busy around the clock managing this new chaos for us. So that being said, here's what it looked like, the Mars 2020 program. I said the cruise stage was, you know, intended to be just used as is, but then we had the vendor who made the solar arrays went out of business. The vendor who made the thrusters, this pocket right over here, a thruster to help control, they didn't make that model of thruster anymore. So we had to redesign that interface. We had to redesign the whole solar interface with a new vendor. Now I mentioned that the parachute, that was intended on redesign from the beginning. So we had a whole new test program to, validate what we redesigned. So that was a big program. The back shell was, again, high heritage. We did actually not have to modify that a lot. The descent stage, even though we had a spare and were reusing that actual physical hardware, we had to make some changes because of some of the change. That descent stage actually mounts to the rover. So because the rover was so different, we did have to make some updates to that descent stage. And as expected, we knew the rover was going to be a significant amount of redesign. One of the things, when you put this descent stage and rover together, this radar area sat below here, and that was the closest and most critical clearances during this separation on the previous mission. And the first thing we did when we started in on this is we pushed this whole front panel out, which pushed all that hardware into this area of the radar. So we had to redesign that radar platform on the descent stage. So those sorts of things were continuous as we matured and moved forward. And we never stopped the program. We have a launch date. As we find these problems, we address them, but everybody has to keep moving forward and maturing their design. I equate it all the time to fixing a car as you drive it. That's essentially what we were doing. And this helicopter shown here was never part of the original plan, but we down the road had decided to add it. To manage all this chaos, we needed some structure. And it turns out your organization helped us out tremendously with that. Turns out the ASME standards that we already used and are on the face of our drawings, the ASME Y14 100 is the governing standard for our whole design environment. And part of it talks about configuration management. And so the thing that got us through with sanity, and low risk was following those standards. One of the standards states that, if you change any change to form, fit, or function post baseline requires a new part number. Now, one thing the ASME standards are popular or known for also is being vague at some points where you might want them to be more specific and crucial. There were some areas like that affected us. For instance, in this statement here, change to form, fit, or function post baseline requires a new part number. Well, what's baseline? We would have liked them to have said specifically, this is what baseline is. Turns out it's different for every company and every type of production you're into. But essentially, when that baseline was drawn in the sand, anything after that, you need to, if you're making a change that changes form, fit, or function, you have to give it a new part number. So I had to make some decisions here. I decided for sure baseline for us was launch. And so the previous launch had set the baseline for a lot of the stuff we were using. If we changed form, fit, or function, we gave it a new part number. And so we even had some choices there that were critical. We could have given it a new part number by adding additional dash numbers, but that turns out was more complicated than just giving a whole new part number altogether. And that's what you see here. And that's what we end up doing. There are special cases where we use the original part and added multiple dashes, but that was rare. The other thing that was a challenge for us as we began to reuse this hardware, again, since we were a one-off prototype operation, we would build spacecraft, we would test a spacecraft, and it turns out we'd find things that were wrong, and we'd go back and fix the design, actually change the design based on the things we found out during testing. But sometimes something didn't fit, for instance. And let's say it's mounting with 4 holes. We would just say, oh, well, all you have to do is open up one of those holes, take a reamer, make it wider, and all of a sudden it fit. Well, that's not a design change. We had to classify that as a build change and keep them separate. So build changes we didn't put back into the design. But let's say that same thing you mounted broke during a test. We decided the loads were too high, so we added, instead of 4 holes, we added 2 more, so there were 6 holes. That's a design change. You go back to the design and you make that new design have 6 holes. So we had to get good at separating those sorts of changes into this process. And you stir all that together, and that was our life on the edge from concept to launch. And we made it through that. We had some therapy going on. We had some comforting each other. We had some trials and tribulations. We had things that worked beautifully. And it turns out that brings a tear to your eye, just like when things break. You can't tell the difference sometimes. So all that being said, I wanted to just kind of share with you a case study of the type of challenges we ran into throughout, and they're typical, not just on this mission, but most of the missions we do, especially landing something on another planet, that's very difficult. So here was a case study for a particular challenge. I showed you that we talked about that descent stage and that rover. They're bolted together until they get to near the surface of the planet. Then they separate and go into what we call a sky crane configuration. Well, most of our separations are controlled by guide rails. And so those guide rails keep things from flopping around as they separate. Well, this particular separation, we couldn't use guide rails. And it was an unguided separation. So literally just gravity and the thrust from these engines are going to cause that separation. So when you have, you actually have wind and turbulence and all those things going on and motion here. So clearance, we could not absolutely could not tolerate recontact of these two elements as they separated. That took a significant amount of our resources managing from beginning to end. And by end, I mean launch. So this was one of the biggest challenges. And we're going to walk through this use case and kind of show you what we've done before and the new techniques we use here. Again, some of the things that affected this separation clearance issue was the growth in the rover. We talked about that. It was already marginally close on the previous mission, and now it's closer because of the growth. The biggest thing that keeps us up at night is we're not able to test what you see here on the screen, this sky crane maneuver. We can't test on Earth. We don't possess or can't recreate the Mars atmosphere and create a full test of this sky crane. So we could test different pieces of this process, for some loads here and there, things like that, but we could not test this whole process. So we relied heavily on analysis and simulation to validate this process. So that's what we're going to talk about. If you look for this same scenario or challenge on MSL, we created what we call these separation envelopes by hand. We manually walked through the design, the CAD model of that sky crane vehicle, and found where things were close. We measured, we came up with a criteria of when something was close enough to be concerned about, and this, that, and the other. And we created these colorful envelopes you see here by hand with following this logic here on this top chart. This logic was based on some simulation and analysis of that separation, but we created this by hand. Fast forward to Mars 2020, we were able to run a significant set of Monte Carlos using atom simulations. And that's what you see, these tornado-looking curves here. What you see, each one of these curves is a set of over 1,000 points along that curve. That one curve is called a trajectory being simulated in atoms. So there was 1,500, I'm sorry, I think I have my numbers backwards. There was 1,500 points along that trajectory and 1,000 of these trajectories. When you add all that up, you're talking over 1 million points. And what we were able to do, it turns out we had a tool we were using just for visualization, Team Center Visualization Mockup is what it's called. It had the capability of reading in the resulting atoms file here and actually move our CAD assemblies of those elements through these trajectories. And in that movement, create a swept volume. And you're looking here at the resultant swept volume of running through that over 1 million points. There were some challenges. It took us months to get to the point where we could duplicate this effectively. For instance, the tip of this tornado down here is where all the trajectories started. And as they moved away, they went along their own path. Well, what would happen in this analysis is we would get to the top of the trajectory and it would snap right back to zero to start the next trajectory. And that snap ended up being part of this envelope. Well, that was incorrect. So we actually had to write a script to double up, actually run along the trajectory and run exactly in reverse order back down that same trajectory in order not to create false positives in this envelope. So that doubled over 3 million points now in this whole process. And I tell you, sometimes discovery is by accident. And there was certainly a couple of cases here. Most of our tools couldn't have handled 3 million points of anything. And I was running this on one of the computers I had, and I couldn't get it to complete But I just had a sneaky suspicion with 3 million points, it was based on some sort of computer resource like memory or something. But the error messages were not telling me or giving me a clue as to what was going on. So I took a guess, and I had a much stronger computer. I won't call it a supercomputer, but for this example, that's what it was for me. Had a significant amount of RAM and so forth. So I ran it on there. I didn't get the error message, but it kept running and running and running. And so since I had multiple computers, I said, you know what? I'm gonna just let it run until it errors out or finishes. And I just did my work on my other computer, my other daily work. And it turns out it kept running. A day later, 2 days later, 3 days later, still running, 24 hours a day for 7 days straight. That processed this whole set of points and created that. It took 7, but it finished. And at the end of that 7th day, I don't know if you guys have kids or not, but it was just short of having a baby. You know, I had tears in my eyes. I was so elated that the process worked, because what it meant was now we could capture everything. This previous process we did by hand and by eye, there's plenty of things we could have missed. Here we could capture the whole vehicle through all the possibilities, and that's what we did. So that was a significant breakthrough for us. We put this sort of product back in our design environment, and here's kind of what it looked like. On the left, you see the result of the actual detail running of those 3 million points. That simulation represented the reality of all the possibilities that could happen. In the design process, you want some margin built in, because things change, things come up that you didn't plan for. So we always build in margin to most of our challenges and resources that we manage, clearances being one of them. And so we took, I'm gonna go back a slide. We took this set of curves, the red and the blue where the simulation runs. We built a set of curves that bounded that, but with some margin built in. And we reran it with those marginal curves and got a much more robust design environment envelope of the same thing. So that saved the day. We were able to put that back in the design process and use that to bind all of our design, our hardware design elements. Now, you know, one of our mantras at JPL is not to polish the cannonball. And we try to live by that. You know, I work with such a significant group of smart people, you know, talented in all elements, disciplines, and so forth. So we really could make things better all the time. Give us more time, we'll make it better. That's the problem. We have a launch schedule to meet. So we tend to avoid things where we're just trying to make it better. But there was a case where it came up. The previous example I showed you here, our analysis was, you know, in dynamics, when things move, you can look at it relatively in a couple different ways. So we originally fixed the rover and have the descent stage move away along those trajectories you saw. So people on the rover were saying, hey, we want our own envelope to bound our, you know, clearances for separation. And so we reversed it. We held the descent stage fixed, and we used to reverse those trajectories and move the rover away. And that produced these set of envelopes. So that wasn't polishing the cannonball. It actually was useful in a way those previous envelopes could not be. And now we had both for the full system. And that ended up being just a significant value for us, an improvement over what we had done before. It's not even fair to say improvement. We didn't have this before. And so it was done by hand. Let's move forward. And so since it worked so well for those separation clearances, we had, you know, we had already divided the separation up into 3 categories. You know, separation clearances were for about the first half a meter in separation. And keep in mind, this sky crane configuration was a separation of about 7 meters long on those bridles. So 0.5 meter is not very much, but that was enough for the two vehicles to clear each other. So we called that our separation clearances. Then there was a near field clearance after that. As it continues to grow in separation, it could also swing further, be impacted by the environment further. So we had different set of requirements for those near field separations. And that brought into concern, the radar on the descent stage. The radar is this element up here that looks for the ground and is mapping the ground with these antennas. Well, if the rover's in the field of view blocking that, we're not going to see the ground and be able to tell where we are. That's bad. So, we said, you know what, let's use the same process since we can create these envelopes with the entire vehicle systematically. Let's use that same process to verify the requirements for our near-term separation and our far field separation. So that's what started this process. We had early on, these mobility, as the sky crane started, the mobility would cut loose and drop, and start hanging just by gravity. Well, that swept envelope affects the clearance again in that short-term area. And then there was a requirement that we had to be able to accommodate like 2.5 degree yaw, if you will, of that whole rover. Well, if the mobility sweeping and the rover's yawing, you get this this envelope that looks like this. It's hard to see in yellow there, but as you get down to the far field, that same, take all those requirements from before, they're still in play. Now as you're down further, that rover can also now go 300, rotate 360 degrees. Well, you take that, rotate it 360, you get an envelope that looks like that. So it's clearing our two main concerns, radar, which you'll see in a minute, but also the plume. The plumes from the rockets were the first and biggest concern. That was the concern on the previous mission. And once we found out those plumes were an issue on the previous mission, it took us essentially 2 years to redesign everything so those rocket plumes were not an issue for the rover anymore. So we had to verify we didn't recreate that problem. They still need to clear those plumes. So we use that same process here. And then when you're landing, we had requirements. You have to be able to land on a 30-degree slope, and that rover can swing plus or minus, 1,300 millimeters. So you had a whole new volume. So the progression of it looked like here, from the near field to the far field to the touchdown. And we use those envelopes to validate our requirements. As you can see here, not all the requirements were met. So that was for the plumes, and here's what it looked like for the radar. The areas where we determined didn't meet the requirements here, we were able to disposition almost all of them and say, okay, this is in a low risk area. The odds of this actually occurring at this extreme were low. So it didn't, they just had to move into a posture to accept the risk. We couldn't do any more to the design to fix that, but it became an acceptable risk. That is par for the course for a lot of what we do. When we get to an unacceptable risk, there's bigger, worse things that happen. So we were able to get through that whole process with acceptable risk. So that's just a look at a case study of the typical types of problems. You can't plan for these. They creep up when you start putting things together at a system, subsystem level. And this is kind of the ingenuity and the creativity we use in actually how we go about solving these sorts of problems. And the end result of that sky crane and separation and so forth is and was evident for the first time. Like I said, we carried those entry descent landing cameras to actually capture the footage of how this process worked. We couldn't test it on Earth, remember. We would have liked to, but we couldn't. And we hadn't had it on any previous mission, so we could see how things were. People had to campaign to get these cameras on board. These cameras added no value to this mission. But for future missions, we can now validate. It was kind of like our test program for real during the flight. So what I'm attempt to play here is the video of this actual sky crane event.
Applicant indicates chute deployed.
That the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
So this is the actual camera video, Will.
Solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar
Yes.
down. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from
Confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Well, we just finished watching the replay, Will, and I have to say it's pretty much as exciting as it was the first time.
So yeah, what you saw was a result. People weren't clapping and cheering because they saw the video you just saw. Those videos didn't come until later when things could be transmitted. And but we got the signals that things worked successfully, and that's typically what we were used to. This was the first time we were ever able to see what actually took place. So I've been there 37 years, and by far that was the most exciting footage I've ever seen. And it doesn't get old. I can watch it over and over. And it points to a very successful effort of a large team of people, very talented people, innovative thinking, innovative problem solvers. We use innovative and robust tools to help us solve some of those complex problems. We have an infrastructure that enables efficient capture and reuse of the intellectual property. I say that now. We had to recognize when we started this that we didn't, and we had to develop it over time. But just another one of those problems that we had to solve. And at the end of the day, in our business particularly, you want to celebrate your successes because there are failures too. You want to learn from your failures, but you want to celebrate your successes and celebrate your people. And I think that's a healthy formula. And, we're on and off to the next one and hopefully continue that success. But thank you guys for your time and your interest in, Mars and space exploration. Thank you very much.
Well, thank you, Will. That's just great. Some of the things that I learned from your presentation are about the different windows of envelopes you have to use in the design and how the simulation really changed. To thank you from the Oregon section, we have this certificate of our thanks, and our group leadership team have talked about. We are going to also be giving you a gift membership in ASME for your thanks here today.
Oh, well, thank you very much.